Good day to all. I'm Dr. Ashima Srivastava from Chemistry Department, JSS Academy of Technical Education, Noida. This is my fourth lecture on molecular orbital theory, and in this lecture I'll be discussing the molecular orbital diagrams of heteronuclear diatomic molecules. This lecture has two learning objectives. Number one, to draw the molecular orbital diagrams of three molecules that are nitric oxide NO, carbon monoxide CO, and hydrogen fluoride HF. The objective number two is to discuss the bond order and magnetic behavior of these molecules. Now there is one issue regarding the drawing of molecular orbital diagrams of heteronuclear diatomic molecules, and that is where to place the atomic orbitals of one atom with respect to the atomic orbital of another atom. We cannot place them at the same level since these atomic orbitals are coming from two different atoms. In case of homonuclear molecules, we were placing the atomic orbitals at the same level because they belong to the same atom. But this cannot be done in this case. The answer for this comes from our understanding of electronegativity. The atomic orbitals of more electronegative atom are placed at the lower level on the molecular orbital diagram than those of the less electronegative atom that we can also call more electropositive. Now we will understand it by taking an example of NO. In NO molecule, since oxygen is more electronegative than nitrogen, therefore the atomic orbitals of oxygen will be placed at the lower level with respect to the atomic orbitals of nitrogen. Now let us see the explanation for this in detail. As we all know that electronegative atom is the one that can attract the electron more efficiently towards itself, and therefore these electrons are more closer to its own nuclei as compared to the one which is less electronegative, and these electrons will be of lower energy as compared to that of less electronegative atom, and hence in the molecular orbital diagram construction we will be placing them at the lower position. Now before taking the three molecules for discussion, we will start our discussion by taking one hypothetical molecule AB, and that is a heteronuclear molecule. Now in this AB molecule, B is more electronegative than A. What we notice in this figure is that the atomic orbital 1s of B has been placed at the lower level as compared to the atomic orbital of A. And the reason is that atomic orbitals of B are more closer to the nucleus and hence more stable. Now these two atomic orbitals, since though they are having little energy difference, but they can overlap, and this overlap will result in the formation of two molecular orbitals. One is bonding molecular orbital, that is shown by the symbol sigma 1s, and other one is sigma star 1s, that is anti-bonding molecular orbital. Now since there is an energy difference between these two set of atomic orbitals, there is less strong interaction, or we can say less effective overlap, and hence heteronuclear molecules are little weaker as compared to homonuclear molecules in terms of stability. Let us take our first molecule, nitric oxide. Nitric oxide is having two atoms, nitrogen and oxygen. Nitrogen atomic number is 7 and that for oxygen is 8. So there are total of 7 plus 8 is equal to 15 electrons that has to be accommodated in the molecular orbital diagram of this molecule. In this slide, I have mentioned the electronic configuration of both these atoms, 1s2, 2s2, 2p3 for nitrogen and 1s2, 2s2, 2p4 for oxygen. These are the atomic orbitals in which these electrons are present. Now, while drawing the molecular orbital diagram, what we will notice that we have seen earlier in the previous slide of hypothetical AB molecule, that the bonding molecular orbitals will be more closer to oxygen and anti-bonding will be more closer to nitrogen, since oxygen is more electronegative than nitrogen. Now, this is the molecular orbital diagram of nitric oxide. On the right hand side, the atomic orbitals of nitrogen are drawn. On the right hand side, the atomic orbitals of oxygen are drawn, and on the left hand side, we are having the atomic orbitals of nitrogen. Atomic orbitals of nitrogen are 1s, 2s and 2p. Atomic orbitals of oxygen are also 1s, 2s and 2p. 1s of nitrogen will overlap only with 1s of oxygen. 2s of nitrogen will overlap with 2s of oxygen, and similarly 2p with 2p of both the atoms. Now, the overlap of 1s of nitrogen with 1s of oxygen will result in the formation of two molecular orbitals, sigma 1s and sigma star 1s. One is bonding, the other one is anti-bonding. Similarly, in case of 2s orbital combination of both the atoms, sigma 2s and sigma star 2s, two molecular orbitals will be formed. Upon the combination of 2p of both the atoms, 6 molecular orbitals will be formed, and they will be sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py and sigma star 2pz. You have to remember this, that sigma star 2pz is always placed at the highest level irrespective of lighter, heavier, heteronuclear nuclei. Now, this is the molecular orbital diagram or energy level diagram of nitric oxide. What one thing we notice is that sigma 2pz is placed at the lower level than the pi 2px and pi 2py, and this is similar to oxygen type nuclei. Now, we will start filling the electrons in the molecular orbitals of this nitric oxide molecule, and the first electron will go in sigma 1s and the next electron also in the sigma 1s. The last electron, that is the 15th electron, will enter in the pi star 2p x orbital. Now, just by looking at this molecular orbital diagram, we can calculate the number of electrons in the bonding molecular orbitals and number of electrons in the anti-bonding molecular orbitals. The number of electrons in the bonding molecular orbitals are 10 and that of anti-bonding are 5. So, if I ask you to calculate the bond order of this molecule, it will be 10 minus 5 divided by 2, and that is equal to 2.5. Now, this bond order of nitric oxide is less than that of nitrogen molecule. So, we can say that nitrogen molecule is more stable than this nitric oxide molecule. Now, in this slide, I have shown you the molecular orbital configuration of NO, and along with it the bond order is also written. Molecular orbital configuration can be written in very easy manner just by first drawing the molecular orbital diagram and then just writing it in increasing order. S, 1s2, S stands for sigma. So, we should write one symbol sigma over that, followed by the next orbitals, and here I have written p to px2, p to py2. The p means pi. So, it should be replaced by the symbol pi while you are writing it in your notebook. Now, let us talk about the magnetic property of this molecule. Since this molecule is having one unpaired electron, it means that it will be paramagnetic in nature. The second molecule that we will take up is carbon monoxide. The electronic configuration of carbon monoxide can be written by constructing the molecular orbital diagram of the same. Carbon monoxide is having 14 electrons present in it. 6 are coming from carbon and 8 are coming from oxygen. So, these 14 electrons we will accommodate in the molecular orbital diagram of this molecule. Now, if you recall that nitrogen is also having the 14 electrons, and we may think that we can write down its electronic configuration or draw its molecular orbital diagram on the similar lines that of nitrogen. Now, if we do that, the molecular orbital configuration for CO molecule will be quite similar to that of nitrogen, and the bond order will also come out to be 3. But this configuration, molecular orbital configuration, is not right. This is incorrect. And if this molecular orbital configuration have been correct, then the bond order of CO plus should be reduced to 2.5 and its bond length should be increased, because when we will be forming CO plus molecule, we will be removing the electron from the antibonding orbital, that is pi star 2px. So, bond order will decrease and it should decrease to 2.5. But this does not correlate with our experimental observation. What is our experimental observation? Our experimental observation is that the bond length of CO plus is shorter than that of bond length of CO, and it is only possible when the bond order of CO is more than that of CO, when the bond order of CO plus is more than that of CO molecule. Now, this experimental observation cannot be explained with the help of the molecular orbital configuration which we have given in terms of nitrogen. So, this molecular orbital configuration needs some change so that we can explain the experimental observation satisfactorily. So, what is the explanation for this? The explanation is that for the decrease in the bond length, the electron should be removed from the anti-bonding molecular orbital. Now, in case of CO molecule and the molecular orbital diagram which is similar to nitrogen, when we are removing the electron, we are removing the electron from the bonding molecular orbital, and that is leading to reduction in the bond order. So, we should have that molecular orbital diagram in which the electron is removed from the anti-bonding molecular orbital, and for that we have to raise the sigma star 2s orbital containing 2 electron at the higher level than that of sigma 2pz. When we do this, the electron will be removed from the anti-bonding orbital while forming the CO plus ion, and hence the bond order will increase and it will correlate with the experimental observation, that is shorter bond length. Now, let us look this diagram carefully. What we have done, we have taken up the sigma star 2s2 orbital above sigma 2pz orbital, and that is for the reason that we want to remove the electron for forming the CO plus ion from the anti-bonding orbital to explain the experimental observation of shorter bond length, and that is reflected only when the bond order is high for CO plus molecule. The next molecule or the last molecule of today's class is hydrogen fluoride. Now, hydrogen fluoride is having the two atoms, hydrogen and fluorine. Hydrogen having the electronic configuration 1s1 and fluorine 1s2, 2s2, 2p5. Now, for the formation of HF molecule, the 1s orbital of hydrogen overlaps with the 2pz orbital of fluorine, and rest of the atomic orbitals of fluorine are not at all participating in the bond formation. 1s2 and 2s2 of fluorine atoms are deeply seated in the molecule, and hence they just behave as atomic orbitals. 2p5 atomic orbital, 2p5 means 2px2, 2py2 and 2pz2. Now in case of these 2p electrons, the two 2px and 2py are filled and only 2pz is half filled. This 2pz orbital is capable of combining with the s orbital because of the symmetry reason. 2pz is inclined towards the internuclear axis and 1s is spherically symmetrical. So there is no symmetry problem in the head-on overlap of these two orbitals, and thus 1s1 of hydrogen will only overlap with 2pz of fluorine, which contains 1 electron. Now let us see the energy level diagram of this molecule. On the left hand side, 1s orbital of hydrogen atom is placed, and on the right hand side the atomic orbitals of fluorine are drawn. 1s orbital of hydrogen is having higher energy as compared to all the atomic orbitals of fluorine, and since fluorine is most electronegative atom, so all the atomic orbitals of it are placed below that of with respect to hydrogen. Now what we said earlier, that 1s of hydrogen will overlap with 2pz of fluorine. So two atomic orbitals 1s and 2pz will combine and they will lead to the formation of two molecular orbitals, which are sigma spz and sigma star spz. Sigma spz is the bonding molecular orbital and sigma star spz is the anti-bonding molecular orbital. So from the combination of 1s and 2pz, two molecular orbitals will be formed and they are sigma spz and sigma star spz. Now we have to fill these two electrons in these bonding molecular orbitals, and both of the two electrons, that is 1s1 and 2pz1, will go into the sigma spz orbital. The atomic orbitals of fluorine, that is 1s2, 2s2, are deeply seated and hence they just behave as atomic orbitals. They do not participate in bond formation, and 2px and 2py also are behaving as the lone pair of electrons. They also do not participate in the formation of bond between H and F. And you can see that the energy level of 2px and 2py is kept same even when the molecule is formed. So the molecular orbital configuration of HF is 1s2, 2s2. What are 1s2, 2s2? These are the atomic orbitals of fluorine atom which have not participated in bond formation, followed by sigma spz2. This is the bonding molecular orbital in which both the electrons will be located, followed by 2px2 and 2py2. These are the lone pair present on fluorine atom, exclusively on fluorine atom. So that means that these two set of orbitals have also not participated in bond formation, followed by sigma star spz, that is the anti-bonding molecular orbital, which is vacant. So while writing the molecular orbital configuration of HF, even if we write sigma spz2, it is correct because rest of the orbitals are either atomic orbitals, lone pair of electrons containing orbitals, or the vacant anti-bonding molecular orbital. So sigma spz2 could be the correct molecular orbital configuration of HF. But while writing it in this manner, which has been shown in the slide, it gives the correct and real picture. Now let us calculate the bond order. To calculate the bond order, what we do, Nb minus Na divided by 2. Now Nb, that is the number of bonding electrons in this molecule, is 2 only, that is present in sigma spz, and number of electrons in the antibonding orbital is 0. So 2 minus 0 divided by 2 will be equal to 1, and therefore the bond order is 1, which tells us that there is a single covalent bond between H and F atoms of HF molecule. So this brings us to the end of today's class. In the next class on MOT, we will be discussing the band theory to understand metallic bonding. Band theory is an extension of MOT on solids, and we will discuss it in detail in the next class. Thank you.